On this week's episode of Organic Chemistry Unwrapped, we will be discussing the organic chemistry behind candy.
Ooh. There's nothing kids love more than candy. Whether it's chocolate, fruit, or hard candies, everyone of all ages can say they have a favorite sweet they enjoy indulging in.
Being such a prominent industry, it's important to know how these candies are manufactured and the chemistry behind it.
I'm not playing tricks when I say I love organic chemistry.
This week's episode, we will discuss the chemistry behind manipulating sugars, flavors and fragrances, and colorings, and the physical properties on some of our favorite candies. Hey guys, what's your favorite candies?
I like chocolate.
I love chocolate too. The flavor is so sweet and the texture is so smooth and creamy.
Did you know that the Maillard reaction is responsible for that sweet chocolate flavor we all love?
No, I didn't. How does the Maillard reaction work?
Let's go to the lab and we can learn more. The Maillard reaction results from the interaction of amino acids and sugars. It causes the browning of foods while also releasing new aromas and flavors. In terms of chocolate, this reaction is key to developing its sweet flavor. This reaction occurs in 3 stages, and its optimal temperature is between 140 and 165 degrees Celsius. Now let's go learn the 3 stages. During the first stage, the carbonyl group on a glucose molecule reacts with an amino acid to produce an N-substituted glycosylamine. The second step involves the isomerization of the N-substituted glycosylamine. This reaction is called an Amardi rearrangement and forms a compound called a ketosamine. Lastly, to produce the chocolate flavor, the ketosamine products will dehydrate into reductase.
Because the Maillard reaction is so versatile in the sense that it produces so many different flavors and aromas, there are specific conditions required to produce the flavor of chocolate. As Evelyn stated in our case, the desired end product of the reaction is a reductone, or dihydroreductone, which can only be developed at a pH of 6 or above.
Wow, I never even thought about where the flavor of chocolate comes from. What about other flavors like wintergreen?
Well, the flavor of wintergreen can be contributed to the chemical methyl salicylate. In order to produce this flavoring, salicylic acid is mixed with methyl alcohol and also mixed with sulfuric acid.
Wait, sulfuric acid and alcohol? Aren't we making this candy for children to eat?
Yes, but the way chemistry works, reagents don't always carry over the same properties as their products. For example, in the drug industry today, a lot of the peptide-based drugs are initially cleaved with toxic solvents. That doesn't necessarily mean that those drugs are toxic because of their reagents.
Enough about drugs and poison. Let's take it back to candy.
Fair enough. As I was saying, this mixture of sulfuric acid, salicylic acid, and methyl alcohol is moved to a reflux container, where it remains under reflux for an extended period of time until all the alcohol is distilled. It then moves to a cooling point, and then finally to a separator, where the separated components are then further moved to a mixing point. It is at this mixing point where it is treated and rinsed with an ether solution. From this point on, it moves on to a second rinsing point, where the H2O flushes out remaining hydroxide and sulfuric acid. It then moves to a further mixing point, where it is treated with 10% bicarbonate, which removes any of the excess reagents left. This remaining ethereal solution is moved to a drying oven, where it is further dried and filtered to produce our final product, methyl salicylate, otherwise known as wintergreen oil. This is what allows us to have some of my personal favorite mint candies like wintergreen mints.
Speaking of mint, mint is actually a separate flavoring used aside from wintergreen in various mint-flavored candies, such as the recognizable red and white striped peppermints. Whether it's peppermints, cough drops, or other related candies, they use a chemical known as menthol to account for this distinct flavor. Menthol is extracted from natural oils from various plants such as corn and of course the peppermint plant. To naturally obtain menthol, leaves of these plants are soaked in an alcohol such as ethanol. As the alcohol is highly volatile, it will evaporate off at a low temperature, leaving behind menthol, which has a higher boiling point of 212 degrees Celsius. The menthol is not soluble in water, and water has a higher boiling point, which is the reason why a strong alcohol is used instead. Once the menthol is extracted from the leaves, they are removed and the solution is filtered of remaining alcohol to get a small yield of the menthol product.
But as someone who loves mint so much, isn't more mint better? Like, how am I supposed to get my fill of mint if the yield is so small?
Well, today, for economic reasons, menthol can be made synthetically. That way you can make more of it and make more money in return. This is when good old organic chemistry comes in. Like many organic mechanisms, the synthesis of menthol from myrcene is named after the scientist who developed it. So in this case, we will be talking about the Takasago process. We start off with a reagent called myrcene, which is a dimer and essential component of oils extracted from a variety of plants. We start off with reacting it with diethylamine and lithium, which allows us to make an addition to the CH2 double bond. Our second step utilizes a catalyst for asymmetric hydrogenation, which then proceeds to react with an acid to form a carbonyl. By now reacting it with zinc bromide, which is a loose acid in this case, we form the hydroxide group, which is finally treated with H2 to target the double bond to form our final product of menthol.
Wow, that mechanism meant a lot to me.
You suck!
I'm glad. It's syntheses like these that allow us to have such an abundance of our favorite mint candies.
Mints and chocolates are great, but what about the flavors of some more creamy and savory candies, like marshmallows and cowtails? You name it.
Well, a lot of these candies use a vanilla flavoring derived from the chemical vanillin. I'm glad you mentioned this because, like in the case with mint, the process to extract natural vanilla from vanilla beans is expensive and time-consuming, which is why much of the vanilla industry today is artificially synthesized. Likewise with mint, the starting reagent comes from an essential oil of natural plants called eugenol. However, a more simple synthetic process uses guaiacol, a yellow aromatic oil derived from creosote.
All right, I don't know about you guys, but some of my favorite candies are the fruit-flavored ones, like gummy bears.
I love gummy bears. My favorites are the cherry and the pineapple flavored ones.
The grape ones are my favorite, but you know which ones I can't stand? The orange ones. What gives gummy bears such distinct flavors?
Well, artificial fruit flavors are actually a combination of hundreds of different organic compounds. However, many of the fragrances and distinct flavors can be contributed to a single ester.
What's an ester?
Well, an ester is an organic compound that contains a carbonyl in our group, as well as another connected by an oxygen. It's used in a variety of industries today, and even is a primary component of wine aging.
Okay, but how do they account for the flavor and smell of grape gummy bears?
Well, the grape can contribute to an ester compound known as methylanthranilate. Okay? No matter the ester, whether it's isopentenyl acetate, which is used in juicy fruit, or even isobutyl formate for artificial raspberry, they all follow something known as the Fischer esterification.
Okay, but how does it work?
Let's go find out. Well, general esters are actually made through a reversible reaction using a carboxylic acid, an alcohol group, and an acid catalyst. So we start with our first step using the carboxylic acid in the presence of the acidic catalyst. So the carbonyl will initiate the reaction by attacking this proton and forming a double-bonded hydroxide group on the carboxylic acid. From here, the double bond will move out, forming a single-bonded hydroxide group, leaving a partial positive charge on the center carbon. From here, the reagent of the alcohol will attack this partial positive by its oxygen. And what we're left with is a tertiary structure where here was the original alcohol. And you can also notice it's also attached by this oxygen. So from here, we do something known as the proton hop, where this hydroxide here will actually steal a proton off this. And what we're left with is a water as a substituent. Now, through organic chemistry, we know that water is a very good leaving group. So we know that this substituent is going to leave. And to compensate for the center carbon, one of the lone pairs off this oxygen will come inward to reform the original double bond we had before. So one of the byproducts that will end up in our final product will be water for this reason. So we are now left again with a double bonded hydroxide group, and notice that it has a partial positive charge. So as it moves forward towards the final product, it's going to lose that H+ ion. And then what we are left with is our final product, an ester with the byproduct of water. And that is the mechanism of the Fischer esterification. Also, let's not forget what manufacturers do to ensure a high yield of this particular reaction. They can either add excess reagents or continuously remove product as the reaction goes on. You may recall Le Chatelier's principle from organic chemistry, and it follows exactly this in terms of equilibrium, where it will completely shift towards the products and towards completion.
Wait, but didn't we do a reaction just like this in our organic chemistry lab?
Yeah, we actually did exactly that. The Fischer esterification is a very broad concept when it comes to organic chemistry, especially in carboxylic acid chemistry.
Oh.
Well, that covers most of my favorite things about candy, but what about the vibrant colors of these candies?
I love the different flavors of gummy bears, but to be honest, I pick my gummy bears based on my favorite color, red.
Really? What do you think makes the gummy bears red?
I know this one. I learned about it in class one time. The colors are artificially produced through food coloring. Each color is created from different organic molecules. Adding these molecules to the candy will alter the color.
Wait, but isn't eating chemicals bad for you? How come we can't just make these gummy bears using natural coloring?
Artificial dyes can be mass-produced at significantly lower prices than natural dyes.
What kind of chemical makes my favorite kind of red gummy bears?
The red color of candy comes from Allura Red AC, also known as Red Number 40. This chemical has been known to have bad side effects due to the compounds in it.
What kind of side effects?
There has been research that links compounds in Red 40, such as benzidine and 4-amino-biphenyl, to cancer and affecting allergies in young children. So be careful with the amount of artificial dyes you eat. They look pretty, but they aren't the best for you.
Hey guys, how many licks do you think it would take to get to the center of this lollipop?
How about you start that lollipop and we'll go study for our Orgo final?